I want to present tonight a project that I've had lots of support with over the years. So the aim of the project is to provide a low-cost 10 megahertz reference for VHF through microwave equipment, and to provide income to support the group's beacon and activities. The paper for GPSDO related to GPS discipline frequency references, traps for young and not so young. The aim there was there seemed to be a big emphasis on GPS locking of radio frequencies. And through the work I did over a couple of years, it became very clear to me that GPS locking wasn't necessarily the flavour of the month that it was being made out to be. Again, there's lots of status associated with GPS locking. People like to be able to say they're GPS locked. It doesn't necessarily contribute to the outcome. But what I'm talking about GPS locking is not the disciplining of a 10 megahertz reference, but those solutions which use GPS to steer, discipline a local reference which is fed into a radio, such as the IC 9700. There are two popular options around the traps that do exactly that. And my point of view hasn't changed. It's really not the way to do it. Okay, this paper addressed the GPS discipline approaches, the alternative solutions for frequency locking of radios, and the limitations. The biggie, of course, is quantization errors, where you can never really get the thing on frequency, jumps which occur when the disciplining is going on, and quite often the time to lock or even incomplete locking when GPS isn't available. Conclusions from that paper was that GPS disciplining lock solutions have shortcomings. Locking to a high stability 10 megahertz reference, in my humble opinion, is the best. And GPS may provide advantages when GPS is available. That is, you can get an improvement over some of the other 10 meg reference solutions if you have GPS available. But the main thing is, you'll see in the presentation, you don't want the GPS to get in the road of a satisfactory answer. Okay, many stations have a major weakness: long settling times. There's a number of examples, including one that Kevin showed me, where there was wandering during the initial disciplining. And of course, it makes that worse where there's a loss of stability if the GPS signal is lost, or because there's a lack of status indication, you don't know that your reference is wandering until you try to work somebody, I guess. Why lock? There's two reasons. Again, this is from the paper. Frequency accuracy, so the other station can find me when I call on SCED, and when operating in digital modes, to be on a specific frequency and to be reported correctly in reverse beaconing. The accuracy really should be within 100 hertz up to 1296. Some people on digital like to be better than that. The biggie, however, is frequency stability. The stability is critical because you want the SSB CW signal to be clear and interference free. You need it so you get optimum decode in digital modes. There's lots of examples around the band, particularly those with IC 9700s that run them with a bit of power and they're aware of the banana-shaped digital curves they end up with because of the drift in that radio. And so decoding others' digital transmissions is not degraded. And the spec there is preferably better than 10 hertz. So it's more important to be stable within a tighter tolerance than it is to be spot on frequency. And these conditions apply for all the operating conditions of the equipment: voltage, ambient temperature, power output, SWR, the radio temperature, and the biggie that gets often discussed now is the fan on off. Kevin and I went through, and also with some experience from other projects that I supported people with, we came up with a list of user requirements, and that is to provide a low-cost 10 megahertz reference for complete shack and rover operation. We want excellent stability, better than 10 parts per billion, that is 0.1 of a hertz at 10 megs. We want high accuracy, and in line with the previous statements, that doesn't have to be as tight as the stability spec, better than 100 parts per billion or 1 hertz. We want sine wave output. Most people seem to favour that, but again, the work we've done doesn't really show that sine wave is a critical requirement. Most of the things, unless you're doing things like tripling for an IC706, your square wave is really what the target device, the PLL or the radio, is looking for. We set on 4 dBm as the target level. We want low phase noise. And again, this is a debatable one. There's a lot of discussion about phase noise, but I think from my investigation, most of the applications, you're feeding a 10 meg reference into another loop or into a digital device that is going to determine the phase noise itself. We want fast warm-up. Some of the early eBay available references, one of the Chinese ones in particular took 25, 30 minutes to warm up. And it's okay if it's a station reference and you're going to leave it up all the time. That's great, but not everybody has that, and particularly in a rover situation. We want multiple outputs. The spec we came up with was 4 or more. I think Kevin indicated 4 to 6. So we snuck in the middle at 5. A lot of the devices, again, available on eBay and other sources, have quite limited power supply range. They can be 5-volt devices. They can be 12-volt, but they only handle from 11.5 to 12.5. We've aimed to go from 12 to 28 volts, which fits in with most home and rover situations. It also avoids the trap where you add some form of regulator ahead of the reference and you introduce noise. It's not hard to do. In fact, in these modules, I found it took some discipline, using that word in a different way, to make sure that there was no noise coming from the regulators. We want low power consumption, and again, some of the options around the traps draw over an amp at 12 volts. We want a small footprint. Our units draw less than half an amp at 12 volts, and at 26 volts, about 300 milliamps. So very happy with the way that came up. And again with input from Kevin, either a box solution or unboxed, so that it can be mounted either in a Go box or mounted in a transverter, and I'll show examples of that later. The other thing that GPS provides is PC time synchronization. It'll give you location, and if you've got a program that'll then take that location and the station you're trying to work, it'll give you a heading calculator. The GPS discipline version must not degrade the warm-up time or stability. And we've put a lot of effort into making sure we meet that. And the software that I use in the little Arduino that does the disciplining has been developed over 3 or 4 years and has been extensively tested for it's got to provide the status of warm-up, the availability of the GPS system, GPS availability and validity, because you can get situations where it's available and it's locked, but it's not valid. The discipline progress and the fact that the 10 meg reference is locked. The accuracy of stability when the GPS is not available. If GPS isn't available, the 10 meg reference should just churtle along, hold its accuracy and hold its stability, in particularly, again, the stability. The Rover solution put up first because it is the simplest, and it's the one where I've used most of these boards so far. That is, we have a 10 meg oven controlled crystal oscillator, and we feed that into a digital LO, a digital PLL, or a SI 5143 or something like that to produce a local oscillator signal. The example I've used here is a harmonic, an output which could be driven into a harmonic multiplier and for a 10 gig transverter. An additional output can be taken out to external devices, such as doing a digital LO, which is synchronized coupled into something like an IC9700. And the two examples I've had here, this is a 23 centimeter SG Labs transverter, and it's a little bit unfriendly. While the Coon will detect the 10 meg reference and swap backwards and forwards, the SG Labs doesn't. So I built the reference, 10 meg reference, into the transverter and amp so that it's always in lock mode. The only disadvantage is with a power amplifier, for example, you got that couple of minutes warm up, but I don't see it as being critical. And then the other one is the multiplier chain out of a 5.8 gig transverter, the ZL digital LO in the middle, and our board driving through that, generating 5616. That's the multiplier board, yes. An extended Rover station might have multiple transverters and radios being locked to the same reference. It most likely will also have GPS receiver for providing time, location and heading calculations on a PC. The time is of course important in digital modes. The option I've taken, and this is configurable, is I use a Neo 6 GPS receiver, and it can be configured for an NEMA RMC, which is the minimum time and position message. So that simplifies the hard work that the PC's got to do in parsing that message, and gives a bit more accuracy because the messages start to come out on the 1 second rollover. But if you've got them all selected, it can be a couple hundred milliseconds before you get the one you want. A whole stack solution. This is where the multiple outputs are required. Here I've shown the output going to transverters, radios, and also, as I do in my shack, it feeds across to the frequency counter and also the spectrum analyzer. So they're locked and gives you that little bit of extra confidence. I was a little skeptical initially with the spectrum analyzer, but I find that with it and using the markers and looking for peaks, it works very well. And again, the NEMA RMC signal out to a personal computer. And this is the box that has been set up to provide the discipline version of the reference, and it has the 4 LEDs to show the status, GPS in, and 4 10 meg reference outs. An initial output is available on a fly lead, not on the edge of the board, so it could be bought out in that box as well. The products. The 10 meg OCXO reference generator, which I've called an OCXO 3. It is, in fact, the third version of the design. And the GPS discipline version uses the same OCXO, but it uses a GPS receiver and a micro to do the frequency measuring and the disciplining. And its designation is GPSDO-1. Now, the detail on the OCXO, it's available in a bare board form. I think I've got another photo. This one is in the half shell, and then on the right, the full oyster shell on that output. It's an oven-controlled crystal oscillator. It's a CDI one for those that have an interest, and we've been able to buy some stock of those at quite good prices, so that should carry the project for some time. It did allow me, by going with one particular OCXO, to minimise the size of the board and the number of alternatives I would have had to handle on the printed circuit board. I calibrated against the GPS discipline reference, and typically they're 0.0 something of a hertz when they're delivered. It operates from 12 to 28 volts. Startup draws 500 milliamps at 12 volts. When it's settled, it settles back to 250 milliamps. It's mainly the oven that's drawing the current, and at 26 volts, that's less than 150 milliamps. There's 4 SMA outputs on the board. One additional output may be added. It's sine or square wave, and the level is greater than 8 dBm. Again, if you've got a particular requirement, can be increased or decreased at order. The CTI OCXO I'm very impressed with. This is the cold start characteristic on the left, and you can see in less than 2 minutes it's settled and is operating very stably, and the graph on the right shows that it's fraction of a hertz in error without any correction. So we've got stability better than 10 parts per billion. The curve there on the right is in fact less than 1 part per billion, but you start starting about those sorts of figures and you draw the crabs, obviously, in our environment. As far as accuracy is concerned, these are the aging figures from the manufacturer of the OCXO. I've got about 4 samples running in my workshop, and I never see them beyond 10 parts per million in correlation with one another. So they're either all drifting in the same direction at the same time, or they are really holding figures that are better than that. And they're the phase noise figures again from the manufacturer. The discipline version, it gets a second board which piggybacks with the OCXO board, and that piggyback board adds the Neo 6 GPS receiver, an Arduino Nano microprocessor running 5 volts and 16 megahertz, because it's actually counting the reference. It has to be one of the higher clock frequency ones, because the Arduinos have limitations on their counting hardware. And that supervises and disciplines the OCXO. 4 outputs, the same arrangement as the OCXO, because it's using the same board, of course. 4 outputs, 1 additional output may be provided. Sine or square wave operates from the same supply. In fact, the power supply on the OCXO feeds the micro and the GPS. Startup current less than 500 milliamps. The load on the micro and the GPS is very low, and they're the total settle figures. We've got a green LED, which shows the unit has supply on it. The Neo 6 can be configured so only when the GPS is valid does it produce 1 pulse per second outputs. That's an advantage because it is a status indication. So if you're getting 1 pulse per second outputs on the LED, you know that it's locked and valid. And it also simplifies the software in the disciplining micro, because it only gets interrupts when the GPS is valid. We have warning LEDs, a warning LED which is steady during warm-up. There's a 3-minute period, I think, to allow the OCXO to warm up and for the GPS to lock. Neo 6 usually locks a lot faster than that, but it can take longer if it's a cold start. There's a long flash during the course discipline or during the settling, the frequency counting. As I say, I make sure I take a long period of time, up to 5 minutes, to actually count the frequency, depending on which phase of the synchronization we're in. There's a fast flash during fine disciplining, and fine discipline is typically steps that are less than 1 hertz, and it goes off when the frequency is accurate and GPS is behaving itself. And the OK green LED shows the reference is locked, so it's a complement to the warning LED. The NEMA RMC is available at 9600 baud via serial USB. For those that have got applications that run at different baud rates, it can be configured if I have that information when the device is ordered. And that provides the PC time synchronization grid square calculation. Now, this is the heart of the matter. This is the block diagram of the discipline reference. The core is the TCXO, 10 megs, fed out through a low pass filter, and that produces a sine wave, goes to a buffer. And after much experimenting, I use a single buffer, which is capable of driving the 4 outputs, and each of those have their 50 ohm source resistors in them. The output from the low pass filter can also be fed out as that 5th output. Otherwise, it's terminated either in the board or at output 5. The output from the TCXO is taken through a JK divider, and that's again a flashback to the 1960s. And that produces 5 megs, which is in the counter range of the Arduino. So we get one pulse per second interrupts into the micro, and it counts the number of counts by overflow and residual over a number of periods, typically 30 seconds. So there's good averaging going on there. And then once the system is locked in course, it drops to counting 10 periods, and it actually does a rolling error count so that it's counting the rolling error at 100 megs. So it's very accurate. I'm very happy with that. The output is a PWM output fed through a low pass filter, and that matches very well to this particular TCXO. A lot of other TCXO need more than the 5 volt control voltage to feed them. The OCXO, how is it different? It's low cost because we're trying to make some money. It comes in better than the market rate, but you don't get them for 2 and 6, I'm afraid. It's calibrated against the GPS disciplined source, and from my experience, it'll hold better than 1 hertz for years. Wide power supply range, sine or square, 4.8 dBm outputs, 1 additional available, low power consumption at startup and later. So that's all a recap of where we've been. And they're the 2 boards, the bare board and the case version. The GPS discipline version builds on the OCXO with an EO6 GPS receiver and an Arduino Nano. When it starts, it actually uses the previous calibration values. So that once the thing has gone through the disciplining phase, it stores the calibration values in E squared prime. And unless there's a major error after the warm-up period, it doesn't attempt to do any corrections. So there's no wandering or instability that we've seen with some other devices. There's no GPS discipline until after the startup delay and a valid GPS lock. The frequency is measured against the GPS 1 pulse per second timing pulses over 30-second periods, and that's for the course calculation. No course discipline adjustments are applied until a large area is confirmed. So it's unusual to get it to go into course adjustment, but if it finds it is after 2 or 3 counting cycles, it will start to apply, but it'll still be holding that warning lamp LED flashing to show that it hasn't settled yet. The frequency for fine is calculated over 10 count periods. So that's over 300 seconds with a rolling error. And that rolling error, if it gets outside bounds, corrections applied and the rolling error is cleared. So there's another 300 seconds before it could make another correction. And the fine discipline adjustments are applied in steps which are transparent to normal digital operation. Maybe not at 76 gig, but they are smaller than 0.4 hertz steps, so you can do your sums on that to see if they would be a concern to you. LED status indicators have GPS valid, frequency accuracy and reference lock, and the USB broadcast. So they're all things that I believe make the product different from a number of offerings, and it provides supply for an active aerial. I wouldn't recommend you use a patch aerial at the module. In most environments, it is satisfactory, but the patch aerials on a 6 metre, active patch aerial on a 6 metre cable does a lot better job if it can see a bit of sky. The models and pricing. The 10 meg oven control reference is a bare module, $85. Module in the enclosure, $95. The GPS reference is in a die-cast box for $195. One I didn't mention in the explanation was one I picked up this afternoon that was in Kevin's user requirement list, and that is for those that already have a reference, but it hasn't got enough outputs. We have a module, we've got a limited number of them. There was only one in a panel of about 10 of the other two modules, but I have a number that can do a distribution amplifier, including a low pass filter. So if you want a distribution amp, we set that price at $55. And then shipping, well, you can't ship anything for nothing at the moment, so I've allowed for a post-pack. We might be able to sharpen that price depending on our experiences. Yeah, thanks to the President for his support and encouragement with loading me with a GPS Tech paper, which I quite enjoyed, and first time at Gips Tech was a good experience. And for the assistance of developing the user requirements, and he's also put a fair effort into the reference for testing, and there you can have that as well. And also to some of the others around the traps, John, MJF, Ron, CRO, and Frank, who have all ended up with projects where I've been able to fine-tune the user requirements, and they've allowed me to test prototypes in their various transverter and radio projects. There's been encouragement from the groups for their inquiries and the support for the group project. The models and pricing. The 10 meg oven control reference is a bare module, $85. Module in the enclosure, $95. The GPS reference is in a die-cast box for $195. One I didn't mention in the explanation was one I picked up this afternoon that was in Kevin's user requirement list, and that is for those that already have a reference, but it hasn't got enough outputs. We have a module, we've got a limited number of them. There was only one in a panel of about 10 of the other two modules, but I have a number that can do a distribution amplifier, including a low pass filter. So if you want a distribution amp, we set that price at $55. And then shipping, well, you can't ship anything for nothing at the moment, so I've allowed for a post pack